Hello, this is the keynotes video for week 2. We're going to write down a series of good notes for us. The big heading for us this week is bonding, so we're going to get that written down. The key idea with bonding is that all atoms, they have a desire, they have an urge in them. All atoms aim to get the electron configuration or the electron arrangement of their nearest noble gas. The noble gases don't form bonds. So we probably need to put in brackets afterwards. The noble gases don't form bonds. So they're special, and basically every other atom is aiming to be special. Unfortunately, all the other atoms will end up forming bonds as part of trying to become like a noble gas. So, how do they get the electron configuration of a noble gas? If they're a metal, then their nearest noble gas tends to be 1 or 2 or 3 atoms back in the periodic table, so they will tend to lose electrons. And if it's a non-metal, their nearest noble gas tends to be the atom after, or a couple of atoms after, or 3 atoms after in the periodic table, and they will tend to gain electrons. So if we have a look at potassium metal, which is K, reacting with fluorine. Okay, if we go up here, we might want to really show this. So we have our potassium atom. So potassium atom in the middle has got 19, you can see from the periodic table it's the 19th element. Potassium atom's got 19, whoops, I'll see if I can rub this out and write this better in for you. It's got 19 protons. I'll just write P for protons. That saves me drawing every little dot out, and it's got 20 neutrons because its mass is 39. So feel free to look at the periodic table to convince yourself of that. And then it's got the K shell. Right? In its K shell, it's going to fit the first 2. Then it's got the next shell that fits 8. So we're now up to 10, all up. Then we go to the next shell, which also fits 8 in. So we're now up to 18. And then it has the last shell, which is going to be KLMN, and its N shell only fits 1 electron in. Now, its nearest noble gas is the element before it, which is argon. And what's interesting about noble gases is they always have a full shell. So potassium wants to get rid of this annoying extra electron floating around in its outer shell. And then we get to fluorine, and fluorine's got 9 protons because it's the 9th element. Get that written nicely. 9 protons. And it's got 10 neutrons because its mass is 19. And around it, fluorine will have the 2 in the K shell, just like potassium. But this time we only need to put 7 more electrons in. So fluorine's got a space in its L shell for one more. So what basically happens is this electron from this goes over there. So potassium loses its electron and fluorine gains. So that means therefore potassium looks like argon, which has got full shells everywhere, and on the outside fluorine looks like neon that's got full shells everywhere. They've now both got full shells, in the case of potassium by losing the extra one, in the case of fluorine by gaining that electron, and they're both happy. Therefore, at the end, if I move all of this down, I'll just see if I can do this, move this up some more, and move this up some more. Therefore, at the end, this fluorine atom has now gained its electron, so the fluorine atom becomes negatively charged. It's got an extra electron. And this one over here becomes positively charged. Because now there's more protons than electrons when it's lost its electron. So when this basically goes over here, then this is now positively charged. So we would write this as K for potassium, put a plus there to show that it's got a single positive charge, and we'd go and write this as F, and we'll put a minus sign over here too. I'm showing that it's got a single negative charge. We call this, when there's positive charges, a cation, and we call this one, it's negatively charged, an anion. So curious about why they call that. When you put electricity through a ionic substance like this substance, the cations are attracted to the negative electrode, which is called a cathode, and the anions are attracted to the positive electrode, which is called the anode. That's where the name cation and anion comes from. And in terms of the actual formula for the whole thing, we would say the formula is Kf, one of each. Let's go and now try a different one. So we'll go to a new slide for this. So e.g. our second example. In this example here, we will react magnesium. Now magnesium will lose 2 electrons because it's in the second group on the periodic table with fluorine. We'll just go and see why. So we'll just go and draw that up. So magnesium sitting down here. Magnesium has got 12 of each, 12 protons, 12 neutrons. It's got 12 electrons. We'll stick a couple in the K shell, give it an L shell with 8 more. 1, 2, 3, 4, 5, 6, 7, 8. And then we'll do a last. I haven't drawn this very well. And there's a couple of extra ones sitting there in the L shell. So that's magnesium. Fluorine is exactly as we drew it before. It's got 9 and 10. So 2 and 7 more. You can probably guess what's going to happen now. One of these electrons is going to, well, both of them from magnesium are going to want to head out to fluorine. But the problem is the fluorine can only take one of them. So the question is, what's going to happen to this extra electron? So what's going to happen to this electron that's sitting here? Because magnesium wants to get rid of this one. So what basically happens, I'll just move everything up slightly so we can see this. What basically happens is another fluorine atom comes along. So a second fluorine atom comes along to the party. So it's going to be the same thing, 9p10n. It's 2. And then it's 7 more. And the other electron will head out to the other fluorine atom. So this one will go all the way down into there. And then magnesium's lost its 2 electrons. It's looking like neon, which is a noble gas, and fluorine happens to also be looking like neon too, because it's gained an extra electron. Fluorine's got full shells, magnesium's got full shells, and everybody's happy. Now we'd write this as the Mg2 plus ion to show that it's lost 2. We'd write this as the F minus anion. This would also be another F minus, and all up the formula for them all would be Mgf2, because we need 2 of these, each one accepting one of Mg's electrons, and the little 2 applies to the thing just before it, which is the F. So you'd read this as 1 magnesium, 2 fluorines. And the name of the compound, and you can use your periodic table to look up the name. For the first bit, the cation bit, we just use the name of the metal. So we'd call this magnesium. And the name of the other one, the fluorine, if you have a look on the very right hand side of your periodic table, you'll see that the F minus anion is actually called fluoride, so the endings change. And this is the same idea for all of them. After a while, and we'll do one more example, you'll see that you don't actually need to draw the atoms. You can just look at the pluses and the minuses to work everything out. So my third example, if I'm just looking at the pluses and the minuses, let's take, for instance, calcium, which forms 2 plus ions, and oxygen, which forms 2 minus. We can see that calcium's got 2 to give, oxygen's got 2 to receive, so the formula, they produce something called calcium oxide, CaO, which we would call calcium oxide. But if I take something like lithium, which is a single plus, and oxygen wants to grab 2, but lithium can only give 1 away. So therefore I'll need 2 lithium atoms involved, each giving 1 away. So therefore I've got 2 lithiums and 1 oxygen, and this we call lithium oxide. We can also get groups. So for instance, I can get sodium, which is Na+, and it turns out that some of the anions aren't just a single atom like we've been dealing with. In fact, sulfur and 4 oxygen atoms hang around like a gang, and they act as though they're an individual atom, and that's called a sulfate anion. So there's sulfur, 4 oxygens, and overall they want to grab 2 electrons. So when I do it this way, I'm going to need 2 sodiums, each giving 1 electron to this whole gang called sulfate that needs 2 electrons to hang around. And if I look at my periodic table, it's just called sodium sulfate. You might be tempted to call it disodium sulfate. Whoops, I've made a really serious error, so please go and fix this up. When I write it down like this, I don't need to put the charge on, so that once I've worked out what the formula is, I don't write the charges on, so I wouldn't write it as 2 minus there. So that's a bit of a boo-boo by me. So please make sure that you get rid of that. And it's similar for all of the other ones. And you might be tempted to say, well, there's 2 sodium, so I should be calling this disodium sulfate, just like I've got carbon dioxide for CO2. If there's only one possibility, which in this case, this is always a formula, there are no other possibilities, people don't bother to put prefixes. But if I've got a compound like carbon dioxide. The reason why I call it carbon dioxide rather than carbon oxide is because there's more than one possibility. There's also another compound, CO, that's carbon monoxide. So we might just put a note down, note you don't need to use prefixes. To use prefixes, and we'll just write down what the prefixes are. Mono is 1, di is 2, tri is 3, tetra is 4, pent is 5, hept is 7, oct is 8. Similar to the way we name things like heptagons and octagons and things in maths, you don't need to use prefixes, etc. if there is only one possibility for the compound. There we go. We're now going to look at the difference between covalent ionic bonds. We might even put a new heading up here, covalent versus ionic bonds. So ionic bonds are between metals. The metals are the cations. Put underneath cations. And non-metals. Remember, the anions can sometimes be a group of atoms. So that's what ionic bonds are. Covalent bonds are between nonmetals. So the covalent bonds, they involve sharing. So there's not the giving and the taking, sharing electrons. A good kind of diagram to explain it is what's called the Lewis diagram. So that if, for instance, I've got, say, carbon and chlorine atoms, I might do fluorine, which is Teflon instead. Carbon reacting with fluorine. Don't know why I've changed colour there. You can actually use Lewis diagrams. So I'll draw the carbon in black, and carbon has got 4 electrons in its outer shell. So I can just do 4 little dots for its 4 electrons. Fluorine has got 7, so fluorine wants 1 more. So what happens is fluorine is, I'll draw fluorine in red. Fluorine is going to be here, 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 and fluorine is going to have 7, and then it's going to use the 8th one from carbon to share. So 1, 2, 3, 4, 5, 6, and the 8th one is a black one, which is a carbon one. So Lewis diagrams can be quite helpful here, because Lewis diagrams just show the outer electrons. They don't have to show all of them. You can start to see here that next to the bond between the carbon and the fluorine atom, the fluorine and the carbon atom are sharing those 2 electrons, one from the carbon, one from the fluorine. So rather than giving or taking, it's just sharing. So if you want to go and work out, is a particular bond going to be a ionic bond, then you find out, is there a metal part of it? If there's a metal part of it, then you know it's got to be ionic, and it will involve cations and anions. If it's made up entirely of non-metals like carbon and fluorine, then you know it's going to be a covalent bond. And as I mentioned, covalent bonds are very easily drawn using these Lewis diagrams, which is a lot easier than trying to draw every single atom. In the Lewis diagram, it's often useful to use different colours to represent what's going on, so that I've used red to show the fluorine, so you can see which ones originally came from the fluorine, and I've used black for the carbon, so you can see which ones originally came from the carbon. As well as this, we're now going to go and look at different intramolecular forces. New heading, intramolecular forces. These are forces between molecules. So we're not talking about forces between atoms here. The first kind of force is what's called the van der Waals force. And the basic idea is that even neutral symmetrical molecules, so even neutral stay there. Symmetrical, so molecules experience fluctuations in the location of electrons. So that even though overall they are neutral, sometimes they are for a few seconds a bit negative, and then the electron's somewhere else, so for a few seconds that little region is a bit positive. To temporary regions of positive or negative charge. And this can attract other molecules. So even though overall they're neutral, temporarily they're not neutral, and therefore temporarily the negative bit of one molecule can be attracted to the positive temporary bit of the other molecule. So one example of this is that the kind of greasy, oily stuff that lizards put out when they're trying to climb walls, the actual forces that hold the lizard's foot with this greasy stuff onto the wall that they're climbing, it's all to do with these van der Waals forces. So they're not as strong as the forces between molecules. And we actually need to change the title here, and I apologise for this. It's actually called intermolecular forces. Fix this bit up. Changes. I wonder if I can use a bigger one. I'll just cross it off. I apologise for this. It's actually called intermolecular forces. They're between molecules. I made an error here. The second one that we get, I'll do on the next page. The second one we get is hydrogen bonding. And with hydrogen bonding, very electron grabby elements, and we call them electronegative elements. I call them electron grabby elements. Electron grab is a slightly weird word, so we'll change that to electronegative elements. These ones create a strong negative charge around them. Which means the rest of the molecule is strongly positive charged. And so that we end up, say with water, I've got oxygen connected to two hydrogens. This end of the water molecule is going to be very negative, and this end is going to be very positive. So if I then have another water molecule next door, then this water molecule, this end of the water molecule, the oxygen end, will be attracted to the hydrogen end of the other molecule, because this negative over here is attracted to this end of it. So that between these molecules there'll be a force. The oxygen of this one is attracted very much to the hydrogen of the next thing, of the other molecule, so that there's a kind of attraction between the two molecules. There's nothing to do with inside the molecule. There's obviously stuff going on inside the molecule that we've already had a look at, but this is between the molecules, which makes water stick together more, which gives it a higher boiling point and things like that. And generally speaking, hydrogen bonding is confined to mainly confined to oxygen and fluorine. They're the ones that are the really grabby ones, which explains why these particular compounds have different boiling points and things from the other ones, because there's more force between the molecules. If you want to go and find out more about hydrogen bonding, then you can go and look at other websites and things like that, and they will explain it in more detail to you. We've also got to look at isomerism, but I think that is actually quite well explained in the task. And if you, again, want more explanation, then go and look at the web links and other things that we've provided for you. So this concludes the notes for this week. Again, some of it you may know and not need to take down. It's entirely up to you.